This video is to cover section 3.2, the fundamental theorem and anti-differentiation. The objectives of this video will be to cover the fundamental theorem of calculus part 1 and part 2, and to define the antiderivative. The fundamental theorem of calculus part 1 says that the integral from a to b of f prime of x dx is equal to f of b minus f of a. Capital F of a and f of b are the antiderivative. This says that what we said before, the definite integral of a rate from a to b is the net y units, which is the change in y that accumulate between t equals a and t equals b. An antiderivative of a function f of x is any function capital F of x where f prime of x equals f of x. The antiderivative of a function is a whole family of functions written f of x plus c, where f prime of x equals f of x and c represents any constant. That's because if you take the derivative of c, it goes to 0, so you have a family of functions that would satisfy being the antiderivative of a function. The antiderivative is also called the indefinite integral. The antiderivative of f, or the indefinite integral of f, is the integral of f of x dx. This notation resembles the definite integral because the fundamental theorem of calculus says antiderivatives and definite integrals are intimately related, but in this notation there are no limits of integration. So when there's no limits of integration and you're taking an indefinite integral, you need to always remember the plus c for the family of functions that satisfy the antiderivative. The integral symbol is called the integral sign. The dx on the end must be included. I like to relate the dx to a period on the end of a sentence. The question of an integral isn't done until you have the dx. It also indicates to the reader or the person performing the calculation what you're actually integrating with respect to. This will make more sense in chapter 4 when we start talking about derivatives and integrals of functions of more than one variable. The function f of x is called the integrand. I've used that notation in the previous video. So you have your integral, integrand, and your dx is kind of like the ending of your sentence. Another way to think about the fundamental theorem of calculus is to solve the expression for f of b. The definite integral of a derivative from a to b gives the net change in the original function. And so we can say that f of b equals f of a plus the integral from a to b of f prime of x dx. The amount we end up with is the amount we start with plus the net change in the function. This lets us get values for the antiderivative as long as we have a starting point and we know something about the area. So right now we're still just working with graphically and numerically instead of the formulas of the antiderivative. That will be covered in the next video. Let's take a look at an example. Suppose capital F of t has the derivative f of t, little f of t, and that's shown to the right. So I've notated on the graph that the red curve here represents little f of t, and its antiderivative would be f of t, and we know that the integral is the area under the rate of change curve bounded by the x-axis. So that's kind of the association we're making here, is that the antiderivative is the definite integral. So we want to use the fundamental theorem of calculus to find the values for capital F of 2. So the antiderivative evaluated at 2 and the antiderivative evaluated out at 8. And we're also given that F of 0 of the antiderivative is 5. Note that we don't know that from this graph. That has to be given information. So just to recall from our previous slide, the fundamental theorem of calculus part 1 says that the integral from a to b of f of t dt is the antiderivative evaluated at b minus the antiderivative evaluated at a. And so we're going to use this to evaluate f of 2 and f of 8, knowing specifically f of 0 equals 5. So I'll say the integral from 0 to 2 of f of t dt by the fundamental theorem of calculus part 1 is the antiderivative evaluated at 2 minus the antiderivative evaluated at 0. So two things, I know this value, it's 5 because that's given in the problem, and I actually know this value from the previous video. I know this is just the area bounded by the rate of change curve between the values 0 and 2. So I'll just be looking for this area and I can approximate that using area of a triangle essentially. So let's solve for f of 2. And we see that we have f of 0 plus the integral from 0 to 2 f of t dt. We were given that f of 0 is 5, and then just to highlight again, I want the area of this triangle that's bounded below the curve f of t from 0 to 2. That's a triangle that has a height of 2 and a base of 2. So that would be 1/2 base times height. That's just the area of a triangle formula. And so we're looking at 5 plus 2, or 7. That's the net area. Alternatively, when we are looking for f of 8, we'll start the same way, the integral from 0 to 8 of f of t dt. By the fundamental theorem of calculus part 1, we're looking at the antiderivative evaluated at 8 minus the antiderivative evaluated at 0. We'll solve for f of 8 because that's what we're trying to look for. That's just adding 0 over to the other side, and it looks like I'm flipping it, but addition is commutative, so I'm just sort of flipping the equality around to make working through this a little bit easier. Again, I know f of 0 is 5. It's given in the problem statement, and I can find the area bounded by the curve from 0 to 8. Now, this is going to take a little bit of kind of finagling because I have a triangle above the x-axis. That'll be positive area. And then I have a triangle below and then a rectangle. And so that's how I'm going to break up my area to find the value of the integral. So I have 5 plus the area of this larger triangle above the x-axis. The base is 4 and the height is 2. So we're looking at 1/2 times the base times the height minus the area of this triangle that's below the x-axis bounded by the curve. It has a base of 1 and a height of 1. So minus because it's below the curve. And then minus the area that's bounded by this rectangle from 5 to 8. That has a base of 4 and a height of 1. Again, minus because it's below the curve. And so we end up with an area of 11 over 2. The fundamental theorem of calculus part 2 says that if a of x is the integral from a to x of f of t dt, then the derivative of a is just the derivative of the integral, which ends up being the integrand evaluated at the upper limit. The derivative of accumulation of a function is the original function. I'm going to say that again in words. The fundamental theorem of calculus part 2 says the derivative of the accumulation function is the original function. So given that a of x is the integral from 0 to x of 3 minus t squared dt, we want to find a prime of t. And so the derivative of the accumulation function is going to be the original function, which would just be 3 minus x squared. We'll put all of this together to use in antiderivative formulas in the next section.